Welcome to this module on machine learning. So till now, we have mostly looked at data analysis, right? So all the tools and techniques that we have looked at have to do with analyzing data and trying to understand the data better, right? With possibly the exception of regression. From now on, for the rest of the course, we'll be looking at how you can infer models about the process that generated the data, right, by looking at the data alone. Right? This is essentially the idea behind machine learning. So what we call, even though it's a kind of a fancy name, when you have visions of robots and Terminators floating around in your head, but machine learning is essentially trying to learn models about the process that generated the data from the data itself. Right? So you could look at examples where you learn about how the rainfall pattern varies over a season. Right? So you could say that rainfall pattern is very intermittent over the season. Or you could look at how the temperature of a certain equipment is varying with time of operation. Right? You could say that the temperature is showing a linear growth. Right? It is possible to do this kind of learning from the data, right, by a machine. Right? And this kind of machine learning algorithms becomes essential when we move away from data analysis into either predictive, descriptive, or prescriptive analytics. Right? For example, I can ask what will be the temperature in 15 minutes of a particular equipment. And if I know that the pattern is that of linear growth, I should be able to tell you what the temperature would be in 15 minutes. And likewise, I can ask you what are the areas that are likely to receive rain, right, in the next season. Then if I know what the variation has been seasonally with the data, then I should be able to tell you what are the areas that are likely to receive rain the next year. Right? And so when I talk about prescriptive analytics, so the first two questions I was asking you are more about questions on the system. Right? In prescriptive analytics, we will be asking questions about what I should do in response to the patterns that you are discovering. For example, I can find out patterns in stock data, and I could ask a question, should I invest in this stock or not? Right? For all of these kinds of analytics, right? So we need to have tools and techniques from machine learning. So what exactly is machine learning? Right? So I'll fall back on this old definition from Tom Mitchell. Right? So Tom Mitchell said an agent is said to learn from experience with respect to some class of tasks and a performance measure P if the learner's performance at tasks as measured by P improves with experience. Okay, there's a lot of qualifications here. In the first case, he didn't say a machine, he just said an agent. So in Tom Mitchell's opinion, this applies to all learning agents. It could be humans, animals, or machines. Right? So an agent is said to learn from experience. Okay? So you have to have experience in trying to solve something. And now you measure this experience with respect to some class of tasks. I mean, so it's not that you can learn everything. So you have to be very specific about what is it that you are trying to learn, right? And the performance measure P, right? So you need to know how well you are doing in that particular task that you are learning about, right? And then if you are set to learn if your performance as measured by P keeps improving with experience. It's a very, very inclusive definition of learning. So you have to be very careful when you use this, because you could even apply it to bizarre scenarios. Right? For example, you could think of a slipper, a new slipper, that becomes more comfortable as you keep wearing it. So you cannot really say that the slipper is learning to fit your feet with experience. Right? So you have to be careful about how we apply this definition, but it's a fairly serviceable definition, as we will see as we go along. So the rest of the course, we will be looking at three different machine learning paradigms. Right? The first one is called supervised learning, right, where you are expected to learn a mapping from certain input variables to output variables. Right? You already looked at one example of such a supervised task when you looked at regression. Right? So where the output variables was a continuous valued variable, right? So, and then the input was described by a set of attributes. And if the output is a categorical output, where it could be one of many classes, right? So you see, Is the patient sick or is he not sick? Will a customer default on the payment or will they not default on the payment? So these are like categorical attributes, right? So in both these examples, or the output could be either 0 or 1. You could think of outputs with multiple such levels. In such cases, the learning problem is called a classification problem. Okay? So, but what distinguishes supervised learning from the other forms of learning is that in the form of experience that you will get. Okay? So whenever I give you an input, a sample input, I'll always have an expected output for this input. Right? So I'll give you a set of samples which consists of an input vector and an expected output for that. Okay? And that is what makes this supervised learning. Okay? In unsupervised learning, okay, the goal here is to discover patterns in the data that need not necessarily be any output that I'm trying to produce, right? So there are many different unsupervised learning problems. We will be particularly looking at 2 in this course. One of them is called clustering, where the idea is to find cohesive grouping among the data points that are given to you. So in order to find any patterns that are occurring. So we'll see how this works in a little while. So but you can readily think of the rainfall task that I was talking about earlier. So you can group regions that somehow are similar in their rainfall behavior, right? And the second unsupervised learning task is known as association mining or association rule mining sometimes. Okay, and the goal here is primarily to find data points that occur together or co-occur frequently. So in association rule mining, essentially you're trying to figure out which data is associated with which other data, so which co-occur frequently. So in both of these cases, as you can see, there is no real output that you're expected to produce except to find the patterns in the data. Right? And the third class of machine learning problems, which are called reinforcement learning, essentially has to do with learning how we would control a system. Right? We'll talk more about it towards the end of the course, but roughly you can think of the following problem. Right? So how did you learn to cycle? Right? So it is not just discovering patterns. Right? There is nobody giving you an input-output pairs that tell you how to cycle. Right? If somebody actually does give you an input-output pair, you'll probably not learn to cycle. If your cycle is tilting by 30 degrees to the horizontal, then you should push down with your right foot with so many newtons of pressure. If somebody gives you directions like that, you will never go into cycle, right? So you have to do some kind of trial and error learning. So that's essentially what reinforcement learning talks about. So we'll do a little bit of this towards the end of the course. Right. So the different machine learning tasks that we're talking about, right? So classification, regression, which are essentially supervised learning problems, right? And remember, I told you that you really need a measure by which you are going to decide whether the algorithm is performing well or not, right? And the measure in the case of classification and regression is just going to be error, right? In the case of classification, it will be the classification error, that is how many mistakes you make in predicting the categorical outputs. And in the case of regression, it's going to be the prediction error, which is how far away you are from the actual value that you need to predict. Right? In the case of unsupervised learning problems, it's a little tricky as to what the measures should be, and there are so when we look at clustering and association rules, we'll talk about many such measures in detail. But roughly, in clustering, one of the measures is how tight your clusters are or how scattered they are. I'm talking very roughly here, but we will formalize this as we go along. And in the case of associations, it's more on how confident you are that these two items are associated, right? And what is the fraction of the population in which such associations appear. So that is what we mean by support and confidence. And again, as I said, this is just to give you an idea that for every task you are going to have an associated measure, right? And we will elaborate on the actual measures as we go along. So having said this, there are many challenges that we need to address, right? So the first challenge in any machine learning problem is to figuring out how good is your model. If somebody gives you a machine learning algorithm and say that, okay, here is a model that's been learned by the algorithm, how do you decide how good that model is, right? So you could use the measures that I showed you on the previous slide, but there could be other ways of deciding how good the model is. Okay, so we'll elaborate on this as we go along. For example, you can build a very detailed model that gives you almost zero error on all the data that is given to you at the beginning. But then this model might essentially be useless when it starts looking at unseen data. When I actually wanted to make predictions on data that I haven't seen before, this model might not perform well at all. Right? So how do I look at that kind of a trade-off? So there are different ways of measuring how good a model is. Right? And then given the data and given the class of models that you're going to look at, how do I choose the right model? Right? So that's the second challenge, and many different machine learning algorithms are all about answering this, the choice of the model question, right? But then it's not all about modeling. So you have to be very cognizant of the data that you are operating with, right? So the first question that plagues all of us is, do I have enough data, right? That might surprise some of you who have heard of terms like big data and having excess of data, data deluge, and so on and so forth. But then getting in a supervised learning problem, getting labeled data is incredibly hard. Right? So you have to have an expert that is looking at all the data and then labeling them for you. So getting such labeled data is incredibly hard. And so do you have sufficient labeled data, or can I make use of unlabeled data in a clever way? So these are kinds of questions that we'll have to think about, right? Is the data of sufficient quality? There could be errors in the data, right? For example, age could be recorded as 225, or there could be noise in very low resolution images that you're feeding your algorithm, and so the algorithm is not able to make out what is there in the image, right? Or it could be that some values are missing or have not been recorded in your data, and then your algorithm has to deal with that. So it's a very important question, whether the data is of sufficient quality. And in almost in every large-scale real-life machine learning installation, a lot of effort has to go into cleaning the data, right? So making sure the data is of sufficient quality to feed into your system, right? And so how confident can you be of the results at the end of it, right? It's both a factor of the data quality, the data volume, and as well as the exact machine learning algorithm that you end up using, right? So all of these factors together influence how confident you can be of the results, right? And at the end of it, there is one very important question, right, which typically is not addressed that carefully, is am I describing the data correctly, right? So for example, there are two classes of questions I could ask here. So the first thing is like, do I have enough information about what I am trying to classify, right? Or age and income enough to describe all my customers, or should I look at gender also, right? How would I answer such a question? A lot of it actually comes from the data analysis that we have been doing so far, right? Or age and income alone sufficient to explain all the variance that I see in the data, or should I include another variable in order to make my model more accurate? So such questions will tie back into all of the analysis that we have seen so far. And the next question, which is more of an, it's partly an engineering issue and partly a theoretical issue, is how I should represent my variables. So how do I represent age? That age can be a number, right? Well, age can sometimes be merely a number. But sometimes you can classify age into different levels as young, middle-aged, and old, right? So what kind of an encoding would you choose for representing age, right? And again, it goes back to the data analysis that we have talked about. And so these are things that you have to pay a lot of attention to. And more often than not, when you're looking at simple exercises that you can do on the web, you end up looking at data that is already, where these questions have already been answered and they're given to you and you're able to do it very easily. But when you go out and you're trying to solve your first real problem using machine learning, you'll find that these are very important questions that you have to answer. So in the next module, we will look at more detail at the different learning paradigms that we talked about today.